All right, so today, as I said last Thursday, we're going to do some trial attendance checking, maybe on the halfway through today's class. So I'm going to start the iClicker at some point a little bit later today, so please have it ready on your mobile device. Oh, do that later. And what I want to continue from last Thursday was about the introduction. I think it's really worth setting up the context and some relevant information about why we are taking this first formal method course. The second formal method course will be 4315 in the mission critical system that you guys will have to take in the next term. So let's set up the common context for these two courses, and then hopefully we can touch upon maybe the first bit of the math review, but we'll get there. Okay. All right, we already talked about the learning outcomes last time. We got safety critical system. I'm going to define that in just a moment. And also we got code of ethics for professional engineers. And also formal method. I think that's where we spend a little bit of time giving you the intuition about the two formal methods that we're going to learn in this program. One will be theorem proving in this course in Rodin, Event B. And another one will be the model checking approach in 4315, but you guys don't have to worry too much about model checking just yet. All right? For this course, we don't worry about model checking. Although, in your lab number 2 or 3, I think I will show you this one plugin of Rodin that can do a little bit of model checking to give you some idea. But anyway, we'll see. Yeah, we're going to see some relevant context for a formal method. And then we're going to see verification versus validation. You will hear about these two terms quite often, but you really ought to know what they really mean to say. But, I'm going to sketch some idea for you. And then the final introduction topic will be model-based system developments. So this is really the heart of the approach we are taking for this course. I'm going to get to it, and especially we're going to learn about what does it really mean to be correct by construction. That's something we'll get to at the end of the introduction. And hopefully time will permit. At the end, hopefully we can start the review of math. So this slide here has been already made available to you. Everything that's set over here in the review of math should be already covered in your previous 1090. Maybe the notation is slightly different, which I'm going to walk you through. But I would encourage you to really start studying the slides already on your own. It's quite self-contained slides, so we're going to talk about some more details and some in-depth, some insights of the review a little bit later. Definitely Thursday, but hopefully a little bit today. All right, some very quick reminder. Okay. So your priority right now, of course, attending the lecture and make sure you complete towards lab number 1, even though the deadline is next Friday. But if you can finish earlier and give yourself a little bit more time to digest the material for Rodin, remember I gave you quite a bit of resources to really skim through for lab number 1. So you should really take the opportunity. Especially, I want to draw your attention to this. If you look back to the instruction for your lab 1, there is a document called Summary of Event B Syntax. Sorry, my pencil does not seem to be connected very well. Let me try it again. Sorry about that. It's called Summary of Event B Syntax. The summary of Event B syntax. So this is something that you also want to get familiar with, because later on, whenever you develop any model in Rodin, starting from lab number 2, you are going to need this document handy. All right, and you might need that as well for the programming test. All right, so I'll let you explore that, and then we can talk about it. Maybe after your lab 1 is due, we can give you some highlights. For tomorrow, unfortunately, I have some schedule conflict. I cannot really be in the lab session. However, if you want to speak to me, please make use of my office hour, Tuesday, Thursday, also Monday over Zoom. But tomorrow, we do have the TAs starting to come into the lab to answer your question. One of the TA is very experienced. He actually took this course before. So you actually definitely can ask him anything about Event B, course material, or rodent. So he will be like a good replacement for me. But next week, I will come back to the lab to help you. All right? Just for tomorrow. Sorry, I'm going to miss that. I'm going to miss the fun together with you. Alrighty. Do you guys have any question about the course in general? Anything you want to ask me? Everything's good? Everybody started lab 1, I hope? At least, right? At least you open the PDF, right? That's a good sign. All right. I'll take silence as a yes. Let's now move on to the introduction lecture over here. Let's now start the first one. What is a safety critical system? So there is a difference between safety critical versus mission critical. A mission critical system is what you're going to take in 4315. But let's understand really the difference. Okay? Let's see a simple definition. A safety critical system is a system, and if it fails or if it malfunctions, if it doesn't function as intended, it might cause some consequences. What could be the consequences? It could be, loss of life or injured people. Or it could be some loss or severe damage to some equipment or property. Or it could be some very severe damage or harm to the environment. So these are the very dire consequences. If your system has such dire consequences, your system should be considered as safety critical system. Okay, that's a simple definition, right? And based on this definition, I do have something there on my list. Do you guys have any example you think that's safety critical you want to share? We can just see what you have if they match with any one of the examples I got. Anybody? Safety critical, yes, please. I like it. Yes, indeed. So let me switch to iPad. I'm going to copy down you guys' suggestion. So we talk about safety critical system. Safety critical system. And the one your classmate just mentioned is a very good example, nuclear power plant. And I will give you a relevant one. Do you know the Darlington shutdown system? You know, in Ontario, part of our power source comes from nuclear power plant. And the one that's controlling about the safety of the nuclear reactor is something called Darlington shutdown system. So that one's kind of relevant to the nuclear power plant, which is to regulate itself. Okay, I'll put it here. The nuclear shutdown system. So you can think about the idea is you have your nuclear reactor, nuclear power plant over here. And then you have another separate system over here. This will be the shutdown system over here, which constantly monitors the different variables. And what do you think it should be monitoring, for example? Give me one example. Temperature, I like it, yes. To say, if somehow the shutdown system realizes that the nuclear power plant I'm monitoring has the temperature exceeding a certain threshold, I should shut it down right away for safety. Right? Makes sense. Any other example?
Radiation level?
Sorry?
Radiation level?
Yeah, radiation. Yeah, for sure. You know, for example, you might use the radiation to treat the patients, right? Yeah, that's one thing. Yeah, also we'll put radiation. Of course, it should be properly regulated. Otherwise, you definitely can cause harm or injury or even death. Radiation. Anything else? Yes.
Grounding yourself while you're working with circuits.
The circuit? What do you mean? Sorry.
So like, you know how when you're working in a lab and like when you're working with the circuit, then you have like those ground straps.
I see, but would that be safety critical though? If that one fell, you may argue that your hand might be injured, right? Okay. For now, I'll just put a glove over here. Okay, which might cause harm to the human body. Yeah, I'll just take maybe 2 more. Yes?
Pacemakers?
I like it. Yes, pacemaker. That's really a very classic example. Pacemaker. And as for the you know what a pacemaker is? That's something kind of implant into your heart, right? And then to regulate the heartbeat. And just for you guys' information, I like this being mentioned. If you guys are interested, McMaster University actually has a software certification research group in there. And then they have this so-called pacemaker challenge. I'll briefly describe it, and this is optional. If you're kind of interested in what this kind of challenge is, it really kind of exemplified the kind of a formal method problem we can solve by using the technique we're learning in this course. Of course, this may not be the only technique. The pacemaker challenge goes like this. Over there, it supplies some informal documents about what a pacemaker should be and how it is supposed to function. And then the challenge is, can you present some set of formal mechanism to really certify if a given pacemaker is safe and fit for use? That's a challenge. Not too sure if anybody solve it. It's more like an open-ended problem. It's like an engineering problem that's open-ended. Okay, you guys can take a look just for extra context. Basically given, so once you got some formal mechanism, I'll say formal method over here, if you got some pacemaker product, and then you want to answer the question, is it safe and also fit for use? All right, that's just for your context. Yes? Autopilot or auto driving, for example, right? Very nice. So I'll just say autopilot and auto driving. Okay, I think that's very good. Okay, let me stop here. I want to mention one more, which is very relevant to what we're going to do as a case study after the math review. Another one is something called a bridge controller. And if you're wondering about what this is, don't worry. I'm going to give you some intuitive sketch, and we're going to build a bridge controller for the rest of the semester. So you're going to be quite bored. Well, I shouldn't say bored. You'll be quite, what will be the right term? You'll be quite prepared to build a bridge. How about that afterwards? So our bridge controller. I'll give you some idea what it is. Okay, bridge controller. Okay, I'll set up the context here. Imagine that we have some island. Oh, for example, Toronto Island, right? It's an island there. And then you have the big mainland, for example, Toronto downtown. And the restriction given to you as an engineering problem is we have a one-way bridge. So this is a bridge. Pretend it is one way. And now we have to somehow set up the traffic light. There will be one traffic light over here. There will be another traffic light over here. So basically for cars entering from the mainland to the island, we want to look at this traffic light. For cars in the island, they want to exit from there, go back to the mainland. They have to look at this traffic light. How can we be sure we can build some system model? We don't have to really give the 100% implementation details, but how can we build a bridge in such a way that it is useful for our formal verification purpose? So that's something we're going to solve for the rest of the semester. It's actually very nice case study to learn many good stuff about formal methods, theorem proving, deduction, refinements, and many things. That's something we'll go into. But for now, I just want to give you this very informal sketch. All right, good. Yeah, safety critical system. All right, very nice. And before that, safety, okay, I'll get to the safety critical versus mission critical in just one moment. Let's now move on a bit. And given that you guys will be professional engineers when you graduate, you may consider being licensed by, for example, if you work in Ontario, the authority to license you will be the Professional Engineers Ontario, okay, PEO. I also included one link at the bottom of the slide. You can also click on that, explore a little bit. Maybe you are interested in the licensing process for them. And I want to mention just one idea over here about code of ethics, which means when you are licensed as a professional engineer, what would be your responsibility? I'll just give you some idea over here. So what would be considered as a professional conduct such that it will cause no harm to the society, your employers, your clients, and your colleagues, etc. Okay? So they give you some list. I've just mentioned some item here. So you got fairness, loyalty. Makes sense. You also got fidelity, like dedication, faithfulness to those who surround you. And also you gotta devote to high ideals. And the next two items are more relevant. You gotta be knowledgeable about what's the best practice. Well, we are learning that. We are learning formal methods as a good practice to develop and verify system. So that's about the knowledge part. And the next part will be you gotta be competent. Just knowing about formal methods in a very general sense is not good enough. You have to be able to apply the formal methods into developing and verifying system, like how we ask you to do in the labs, rodent, and also in the programming test to see how competently you can apply the technique, right? So these are the knowledge and the competence are really what we are aiming for, right? And what if you misconduct? What's the consequence over here, right? Let's say you're responsible for building the bridge controller. And at the end of the day, let's say you're confident with your work, you will certify on the document to say, now, me, for example, me, Jackie, I certify and put a stamp with my name to say, now, I certify this bridge controller to be safe and fit for use. But the next day, there's a car crash and somebody die. Oh, what will be the consequence? Who should be held responsible? Me, because I signed on the document for approval. The more minor penalty could be I just got suspended for my license. But the more dire consequence would be, well, I might go to jail, right? So that's why when you actually you are licensed as the engineer, professional engineer, you have to be very aware of how competent you are whenever you actually say, now I certify this particular product for use. Right, so that's why code of ethics is so important, right? If you're interested, also you can explore a little bit further. Here, that's the link. So every province has their own institution for licensing. So PEO is just one example for Ontario. For example, Saskatchewan, they also got one institution there as well, right? Okay, so how do we develop safety critical system? How do we do that? So there are certain industrial standards. So these are the documents that usually you wouldn't see. They are actually access restricted. If you want to see the documents, usually you have to pay, or the company that hire you will have to pay. So these are industrial standards might be released by IEEE or ACM, the prestigious institution. They will tell you in order for you to certify an industrial products, what should be the standard you should be held on those certification process. I'm just going to mention some critical points to you that's relevant to this course. Okay? We don't need to see the document. It's not worth our money or the time to really go over them in the course. All right, so they talk about acceptance criteria for mission or safety critical system that need to comply with. So let's say if you have a system, if you want to accept it for use, what will be the criteria? All right, so just to show you the document, well, in case later on you want to refer to them, maybe for your job. So for aviation domain, like building like an autopilot, for example, right? So this is the document name. So don't worry too much, don't memorize it, just for your information. That's about software consideration for airborne system. That's the one domain. Another domain is for the nuclear domain, and that one is released by IEEE. So in those documents, they kind of outline what would be the criteria for the system to be fit for use. Later on, let's say if your employer wants you to somehow get involved in the certification process for each domain, very likely you will run into these documents. At that point, you will look at them. And then hopefully you can tell them that maybe as part of the certification process, we can use event B, or we can use rodent, part of it, not the whole of it. Okay? All right, so now let's boil down into two important criteria. Okay? I'll mention the two, and then I'll sketch some idea together with you. So number one, the system requirements should be precise and complete. And this bullet point number one might make even more sense after you have taken maybe EECS3342, the software engineering requirements. Right? But I can mention that briefly about what this really means. That's number one. So let's now switch right away. Criteria number one. Okay. So we talk about acceptance criteria. Acceptance criteria. All right, so let's talk about two of them. Number one, the requirements being precise. That's number one. Okay, what does it really mean for precision? Well, easy. There should be no ambiguity. And there should be no contradiction. All right? No ambiguity. And also no contradiction. Okay, let me go a little bit further. What does it really mean? No ambiguities. That means given the same piece of work over here, it shouldn't be that engineer number one look at this and have one interpretation, and engineer number two look at this and have another interpretation, right? That will be ambiguous. If you actually got your requirements presented to you, it should be very clear, should be very precise, no ambiguity. And what about contradiction? Well, contradiction, we can easily understand this as, let's say in your requirements documents, they should not mention something and also something not true. In that way, you just got contradiction, right? That's false. Right? For example, the document might say, I want my sorting algorithm to be as efficient as possible. And on the other hand, it says, I'll be happy if my sorting algorithm is quadratic. They're kind of contradictory to each other, right? Because the most efficient way to sort is not just quadratic. It could be n log n. Right? So precise documents. And this is not something we would talk about too much in this course. That will be in 4312. Hopefully your professor there is going to give you a little bit more practical experience on that. I'll just mention that. All right, so the number two criteria, let's look at the slide first. The implementation should conform to the requirement. This one, I would like to go a little bit deeper by giving you something called commuting diagram. I think you deserve to know this. And what I'm going to present to you about point number two is a very general approach for you to adopt later on if you want to verify anything. Okay? Let me just give you, before that, sorry, there's one thing I forgot, which is about complete. Let me just write it down. And then I'll talk about the bullet point number two. Let me go back to one here. I'll talk about complete very quickly. I forgot about that. Okay, and then also we got complete. And complete is also very straightforward. That means the requirements document should really talk about all possible scenarios the customer really want. It shouldn't be that I try to develop my code according to the requirements, but there's a missing scenario. I simply don't know what to do. The client didn't tell me. I shouldn't assume for them, right? No missing scenario. And as a look ahead, in your lab number 5, the last lab, which we're still developing as a new lab for this year, you can look forward to it. We're actually going to give you some idea how can you check if the requirements given to you is actually complete? Right? That's something we'll do in lab number 5. Simple exercise. All right, so that's acceptance criteria number 1. And number 2, let's now go to this point here. How can we be sure the implementation really conforms to the intended requirements? How do we know? Let's now take a look. For example, how do you solve that pacemaker challenge? This is just like a sketch about one way to think about it. And then I'll highlight how you may actually take this approach further for your own developments or your side projects that you may want to do. Okay, let me open a new page. All right, so our goal right now is to verify if the implementation conforms to the requirements. And remember, we talked about requirements should be complete, it should be unambiguous, it should be non-contradictory. Let's assume that's the case. Let's say you already have done that requirements elicitation. Let's assume. Just for now. For the moment, let's assume it is unambiguous, it is non-contradictory, and also it is complete, just for now. And now we want to see how to solve this problem over here in a general way. Let's now see what the inputs are. Okay. Let's say I have some implementation over here. Let me draw a little bit smaller. Let's say this is my implementation. And this implementation over here could be Java, could be Python, could be C++, you name it. Any efficient language you would like to implement your solution. Anything. Interpretation. And on the other hand, we have some target requirements we would like to verify against. This is on the one hand. On the other hand, let's say we got here another thing over here. So this will be requirements. Typically, they are just like documents. Document, let's say, is written in a way that's kind of clear to you what things are supposed to happen, how things are supposed to work. Oh, sorry about that. There we go. Right? So let's clear the initial setup here. We got implementation on the one hand, which we would like to see if it will conform to the requirements. So, for example, let's say, for example, here. Let's use our nuclear power plant system. For example, let's say we got some nuclear power plant. Not necessarily the entire system, maybe a critical part of it, right? Let's be a little bit abstract over here. Let's say nuclear power plant. And in part of the requirements document, we may have some constraint over there to say the sensor value, for example. And let me put in okay, let's say sensor value is strictly less than some preset threshold. And let me put it in different color for a reason. Let me just put them first. Give me a moment. Okay, like that. Let's say that's still red, and this one here is still blue. Let's say here. Okay, we're good. All right. Now, we got some implementation which is supposed to conform to the requirements. For example, the sensor value should be always lower than the threshold. What we want to really prove is to see whether or not it will conform. That's a question mark. Now, how do we solve this problem in general? The challenge is we set this implementation over here being expressed in some programming language versus this requirements over here being expressed in some informal natural language like English. They are said to be in different semantic domains. So we cannot really try to compare them directly. You cannot really compare two things that are not really in the same domain. You can compare something specified in Java and verify against something also specified in Java. That's okay. But now we got Java and some informal documents. They don't really go together. So we need some massaging over here. That's why you're going to see that I'm going to extend the framework over here underneath. That's something I'll do. But let me write a remark first. What you want to realize is, if you look at the implementation here and the requirements over here, these two. So these two are in this different semantic domain. In different semantic domain. Yeah, this term might be new to you. Semantic domain, it simply means their meanings cannot be really compared directly. You have to translate them maybe into something that's common, so you can compare them. In different semantic domains, therefore, cannot compare directly just yet. Okay, that's an important conclusion. So now what should we do? The solution will be, let me sketch that quickly before I write it down. We want to somehow turn this guy here from Java into something formal. We want to turn this guy here also into something that's formal. And these two, turn this into something formal, turn this also into something formal. And these two should be the same language in order for us to do some proofs. And what do you think this can be? Event B, rodent. Or, as you learn next semester about model checking, for example, your professor might use something called TLA+. Well, that's just another language. Okay, let's now sketch this out. So what we can do right now is we can translate, or you can either say translates, or you can say formalize, either way. Formalize this into some formal spec or formal model. In the case of rodent, we can formulate it as a rodent machine, right? With the axiom, with the variables, with the constant, and etc. Okay? It could be the machine, and also the constants, the variables, and axioms. Right? So these are the stuff you actually write into for lab number 1. And we do something similar as well. We are also going to translate the documents into the same semantic domain. That's why I'm putting them both green. So this will be some property. And do you remember what we said about the property? It's called invariant property for our system, right? That's also something you write into for lab number 1. And this will be, for example, invariance. The thing is, you can definitely have this and this in the same semantic domain, i.e. rodent. So you can now do something about them at the same time, in the same framework. That's the beauty about this approach. So that's why, and then, so here, how do we establish between this and this? We basically, well, in general, we want to say this one over here entails this one over here. You can think about this as more like entails. But in Rodin, we have to do a little bit more elaborate, which is to discharge certain proof obligation, right? That's something we'll also see when we build a bridge. So this will be to discharge proof obligation. And one final remark. Now you really want to look at these two. So this one over here, the formal model, and this one over here, the formal property, they are in the same semantic domain, the same. Right? It's really important to note that. The same semantic domain. Right? And of course, to really go from here to here is also about translate and formalize. Well, the same, okay? The two arrows over here. And I want to fill the gap over here. Let's say you want to take this general approach. Let's say you want to verify something against something. You know that you cannot do it directly. The way to do it is to somehow translate this and translate this into something that's common in the same semantic domain. Event B can just be 1. All right? Now, the question is, how do you go from here to here? Right? You guys are software engineer. If I'm telling you that, well, if you want to translate it, just do it manually. So locate your Java code and then code it directly into Rodin by your hands. That would be one way. But as an engineer, lack of automation is not acceptable. We would like to automate this translation. Okay? To translate or to formalize, right? Either you can go just for manual translation. You want to find out somebody who's very smart and who's very good in math to look at both the Java implementation and the documents over here and translate them into some, let's say, event B, manual. However, it's not a very good engineering practice. You want to automate. So solution number 2, which is way better, automate it. And this is something that's beyond the scope of this course. But I think for you guys, as a competent software engineers, you may want to explore this particular technology beyond the course. Something called compiler. All right? So for automated, so what you really want to think about is how to build a compiler yourself. And I would say it's a pity that we don't really have in your curriculum as a core course for taking the compiler to see how you can build a compiler from scratch. For the CS program side, they don't really have this core course either, but they have an optional choice, EECS3342. So if you really got a scope to take another course, that one would be one of the courses I really highly recommend, which is to learn about how to build a compiler which can really translate from something into something else in general, automatically. Okay? And I can tell you that to really build a compiler, it's basically just about tree transformation. You can turn one thing into a tree, translate it into another tree. Okay, anyway, so that's something I will just mention to you. But for those of you who might be wanting to look into compiler, feel free to have a chat with me during office hour. More than happy to give you some resources. And for the rest of you, this page over here, just to inform you about a very general approach to verify something against something else. Very practical. That's why formal methods is really taking off in the industry. All right. Guys, any question about this? We good? Okay, good. Alrighty. And how do we accomplish this criteria? Okay, so now let's, before we talk about these criteria, we already talked about it, but I'll give you a little bit more from a different angle. Let's now distinguish between safety critical versus mission critical. All right, so now we should do that. And there is one extract from some documents which I've found. I'll give you the source as well. Right, so I'm just going to highlight certain parts in this document, but you can find the documents here. They basically talk about mission critical, versus safety critical, right? So I already put some words on the slide. Let's go over the slide. It's easier for you to read. But I'm going to leave this clean so you can also read it when you study for that. It's very important for the context. Okay, critical simply means important, right? Nothing tricky about it. And so, for example, it's very important for the pacemaker to be successful. Otherwise, the heartbeat cannot be regulated safely, right? And also, well, safety, if no safety, injury or loss of life. And for mission over here, so mission is slightly more accommodating term than safety. Mission simply means this is something that's kind of important for you to accomplish. Does its failure really cause loss of life, for example? Not necessarily always. So that's something about mission, okay? And we'll get to this question here in a moment. I want to show you a little bit more in that extract, and then we'll come back to this question here, okay? We want to somehow formulate the relationship between safety critical and mission critical. We'll get there, okay? I want to prepare a little bit more for the answer. All right, when you look at this document here, so this part I already mentioned in the slide about safety critical, right? And what happened when there's a failure, right? You can read it. And here, let me read it to you. Safety critical system demands software that has been developed using a well-defined, mature software development process. That's what we are teaching you in 3342 and 4315. All right, so that's keep in mind. That's our goal for these two courses. And what I want to draw your attention to is, in one of the industrial standards, they talk about something called criticality levels. That's a nice term to actually know. In order for you to know whether or not your system is safety critical or mission critical, you can think about what's really its criticality level. What if the system failed? How can you really characterize its failure? Okay? You can see we got catastrophic, hazardous, severe, major, minor, no effects, right? You can see there's an increasing or decreasing level of importance over here, right? So the way to really see this would be here. These two correspond to safety critical. And the next two, mission critical. Mission critical system. That's just one way to characterize it. That should give you some idea. If you believe if the particular system you're building, if it fails, is catastrophic. Let's say the nuclear power plant. If it fails, oh, pretty catastrophic. That way, it should be safety critical. On the other hand, let's say you're implementing some financial website for some small company. What if it fails? Maybe wouldn't be some severe, maybe some major loss of money for your small company. In that way, maybe mission critical, not safety critical, right? You see my point? Right, so we got these two notions here, and based on criticality level, it's a very common way to decide how critical it is for your system. All right, for the rest, you can take a look. That's pretty much already covered. Right? I'm going to keep it clean so you can also read it for your information. All right, so now we kind of know about safety critical and also mission critical. Now, let's go back to that question there, which will be a nice preview of our math review. Now, how can we formulate the difference between mission critical versus safety critical system? What will be the relationship between them? Can you use any of the maybe logical operators that you learned before to formulate them? I'll see if anybody can suggest an answer, or I can give you multiple choice in a moment. It might be nice for you to think about it. How do you formulate it? Anybody? Let me help you brainstorm. Oh, sorry, you got. Safety critical implies mission critical. Sounds good. Okay. So guys, in case you're a little bit struggling, think about if I say formulates, you got to think about what operators do you have for formulation. You got conjunction, disjunction, implication, right, etc., right? And it turns out, let me write both down. So we're basically talking about safety critical system versus mission critical system, right? Apparently, we got 3 options over here, and what you said there was actually right. Let me just mention all the 3 possibilities. You can say these 2 are equivalent to each other. One implies the other one implies the vice versa. So this is to say, being safety critical implies that it's also mission critical. And being mission critical also implies it's safety critical. That's option number 1. Option number 2, safety critical system implies mission critical system. Number 3, mission critical system implies safety critical system, right? Now let's say it's a multiple choice, right? And what your classmate just said was 100% correct, right? It turns out this is the right answer, okay? But let's see some very informal proof to show that this is wrong. To show what the other ones are wrong, okay? So let me use maybe, mission critical, yep. So let me use mission critical, let me use pink. And also for safety critical, let me use green. All right, apparently you can use a diagram to show that. That's also to do with a subset, relationship that you also learn in 1090. It's a nice, useful application of that. Think about mission critical system. There are more systems that will satisfy this criteria. So mission critical system is a big set. Let's say this set contains all the mission critical system. A subset of them is going to be safety critical. Safety critical system. For example, the pacemaker. So it is not wrong to say the pacemaker is a mission critical system, but it's not accurate enough. You should really say it is safety critical. All right? On the other hand, we can definitely give you a witness over here that's actually mission critical but not safety critical, right? Whenever you want to kind of disprove some implication, that's what you need. One example could be some financial software for small company. For some small company. Right, you can see here, because we say SCS over here is really a subset of MCS, right? And we know that subset relation in math also corresponds to implication, right? That's what you learn in 1090. We're going to review that as well. I just want to give you some sketch quickly. Okay, it's useful stuff, to know the notions between safety critical versus mission critical. And think about this characterization, right? It's useful to set the context. Any question about this? We good? Let me move back to the slides, and we're done with it. And that's something we just said. Okay. Yeah, and that's the article. That's the extract you can also refer to. Okay, let's now move into how we can use the formal method for certification. Formal methods, basically, we already sketched that last time, so I'm not going to repeat. But it's really about mathematically rigorous way to apply. It could be theorem proving, it can be model checking. Okay, so this is just another industrial standard. So later on, if you want to convince your employer that you want to apply formal methods such as Rodin Event B or TLA plus, once you learn from 4315, how can you show your point? Show your employer this document, DO333. That's really the supplements of some industrial standard which advocates the formal methods usage, right? Just for your reference here. By the way, do you need to memorize the names for these standards for the exam? No. All right? In case you're panicking, right? Don't memorize them. right? I got something better for you to learn. But this is just for context. All right, for methods, and it will be mathematical analysis, and then it will be for the correctness and robustness, right? Just a general term to know. So for methods, it will be for unambiguously describing, because we're using math, which we're going to review. So math is really the only notation where when two different engineers look at the same math equation, there's no way they can interpret the math in different ways. That's why we need something formal. And also it can be precise, and also you can, whatever proofs you may have derived or disprove, you got some witness to disprove some theorem, those will be the evidence for your certification, right? You got something formal to present. And one thing here about safety property, I would like to also give you some visualization. And for this course, we also, the most important safety property we're going to use is called something called invariance. Right? So let's say in the bank example you do for lab number 1, you want to make sure, for example, maybe your customer's balance should be no less than the minus credit level. Right? That's what we did in lab number 1. Right? There should be some threshold of how low the balance can be. So that's like a safety property for the system. But let's visualize this very quickly, which will be very useful for later. Okay. Okay, safety property. So, safety property. Or you can think about it, it's more like an invariance. How do we visualize it? The idea would be every possible states of your system should satisfy the invariance. If there is at least one state of your system that does not satisfy the invariance, it's not satisfied. Okay, it's like for all there exist, right? That's something we'll touch upon maybe on Thursday. Okay, let me write it down. So every possible states of the system should satisfy it. The invariance. That's the definition, right? If there's at least one state, okay. If there is at least one state where the invariance does not hold, evaluate into false. It is not satisfying. An analogy for you would be, let's say you're running JUnit test cases on your Java project. If you have a green bar, that means all test cases pass. If you've got a red bar, that means there's at least one test case that does not pass, right? And to visualize this, let me just draw some diagram here. So you can say, let's say here, if I start with an initial state as 0, this is a little bit abstract just to give you some idea informally, but once we get to the bridge controller system, I'm actually going to give you some concrete state. But for now, let's just imagine that. Okay? So this will be the initial states. And then, let's say some event, 1, happened. So we evolve to S1. Let's make it very simple. Let's say another event, E2, happened. So we evolve to the next states. S2. And this may keep going. Okay? And in the case of reactive system, the number of states you might have is simply infinite because a reactive system never stops. Like a bridge controller. The bridge controller never terminates to function. It will always be there. The traffic light should always be functioning. right? For reactive system, you might have an infinite number of states. All right? So now, how do we prove something for infinite number of states? How do we do that? And you guys learned about this method here back in your math class. Possibly when you learn about discrete math, maybe 1019, 1090, maybe 1019, I guess. Do you remember the technique? How do you prove something that's infinite? Induction, yes, indeed. Right? I'm not going to bother you too much about the formal definition. We might refer to it a little bit later. But for now, let's see the concept over here. Let's say this particular system we are considering is reactive. It never stops. So you've got an infinite number of states. But there should be a certain pattern about how it reacts to the outside. So let's say somewhere we have, let's say over here, somewhere in the middle, we got maybe Si. And then over here, maybe we got another Sj. Right? So, and then here we got maybe Ej. Just symbol, don't worry too much. Okay? So what we really want to prove is in general, given Si, assume the invariance holds over here. And then according to the definition of the event Ej, we want to prove that after the effects of Ej. So we're talking about the transition over here, Ej. The invariance maintain. The invariance holds again. That's the critical step we're going to do. So this is why in Rodin, given each individual events, you actually somehow have to show that each event can maintain the invariance. That's something we'll see when we get to the bridge controller. Okay, but now I just want to mention that. So the main message again for this page over here is to say, number one, you want to understand that invariance is a very strong property. It should be the one that's holding for every possible states, starting from the initialization. Number two, for infinite systems such as a reactive system, we simply cannot enumerate all the possible states. It's just not possible because it's infinite. So the way to do it is similar to mathematical induction. We want to consider all possible states to start with, assuming that the invariance already holds. Given all the possible events that might be applicable or enabled in this particular states, after applying this transition, the resulting state is always holding the invariance. That's something we'll try to do. Okay? I'll make this a little bit more example-based once we get to the bridge controller. But for now, it's also important to understand in a more abstract sense for this. Okay? Guys, anything you want to ask about this? Good? Yes?
Is Ji plus 1 in this example?
Well, it could be. Yeah, you can say that. But here, I just want to say, you got some state here, the pre-state and the post-state. You know, just one way to say two states. Yeah. It could be you can put I plus 1 as well. Yes, you may. Yeah. If you put the I plus 1 here, you might just say EI. Just symbol. Yeah. Good. All right. Let's now move on. Let me say, how about one more thing, and then we'll take a short break. Okay? I think today I'll see if I can get to at least one slide for the mathematical review. I will definitely do the review from Thursday, that's for sure. But I just got a few things to mention in the introduction. Okay, let's do them properly. Let me say one more concept, and then we'll take a short break. Now, we want to talk about verification versus validation. That will be the next topic. Okay? So you will see this slide here talk about verification. I'll get into it. Also, the next slide talk about validation. I'll also get to it. But what's really the difference? Okay, let's sketch the idea quickly. Okay, good. Now, here is how you can understand it. Verification are we building the product right? That's how people like to usually put it. I'll put down the validation so you can compare. Validation, on the other hand, is defined as follows. Are we building the right product? You can see it's an interesting definition actually. Just by putting the right over here versus the right over here, it describes the essence about these two. Okay? Can you see the difference between these two sentences over here, what they're trying to say? Right? So here, for verification, it's more about if our process of building, process of construction itself. Did you follow the right procedure to make sure whatever you have built is really the right one? Sorry, that whatever you have done is really conforming to the requirements. Okay? So over here, there's one assumption over here. Assumption, requirements already given. That's the big assumption. So we are not arguing about whether the requirements given is even correct in the first place. We just take it as is, and we are trying to see whether the final products we actually have got really satisfy the requirements. And let me just distract you a little bit. What we describe over here, this approach over here, this is really verification. In some way, because we want to make sure this Java implementation really satisfies the requirements. So let me put down verification. Not validation. Okay, you can draw the connection here. Let me go back here. Okay, and then for validation, so this is not really about the process itself. It's about whatever you're trying to build against, is it really the correct one? Is that really intended by the customers? Are the requirements given truly intended by the customers? That's why. Are we really building the right product? Let's say somehow you build a very nice, dictionary, let's say, sorted from A to Z, but somehow it's no use because what the customer really intends will be sorted from Z to A. Trivial example, but I'm just saying that you want to make sure whatever product you really built, not only that, you have to make sure the process itself is good, but also the requirements itself should be good as well. It's really accurate. It's reflecting the true need of the customer. All right, so these are the two different concerns. Is it clear about how these two concerns should be separated? Right? Verification versus validation. And for validation, again, you will learn more about it in 4312, I'm hoping. Okay. I want to go over 2 more diagrams and we'll take a short break. Okay, 2 more diagrams. And if you go back to the slides over here, I got verification and also I got validation. The texts are pretty easy to follow, but I just want to give you some sketch over here of these 2 diagrams so you can see, you can try to follow them. Okay. Number 1, verification. And guys, this one here should not be strange to you. We have just built that manually ourselves, right? Remember what we had over here? This guy here basically is corresponding to this one over here, this part over here. You got some requirements, you got something here, and then you want to see whether they will sorry, let me see, I pointed the wrong direction. You got, gotta imagine you kind of rotate it upside down, right? You got implementation here, you got informal requirements over here, right? You want to make sure this conforms to this. That's exactly the problem we had earlier, right? The way to do it is translate this into something formal, translate this into something formal, and then do the verification in this semantic domain, right? That's all we said. Sorry, the orientation is a little bit opposite, okay? But it's really talking about the same thing. What I want to really highlight to you is this. This is informal, and this implementation over here is really in a different semantic domain. And to be realistic, also it has to make use of library classes or library modules. Let me say library modules. For example, if you do your implementation in Java, very likely you don't really invent everything from scratch. You may have to refer to some Java API classes or a different library, or Python. If you do some machine learning, let's say app, you may have to use their machine learning libraries, right? You want to make use of their library functions, okay? So this part over here is about formulating informal requirements into something here, formulating implementation into something here, and what we really want to prove is over here. And typically, what you will get is some proof obligation to discharge. Okay. One thing that's in addition to what we did earlier manually is this one here. Let me explain why that should also be considered. Let's say you're implementing something in Java, right? You're making use of so many library classes, like a scanner, maybe the string, maybe the linked list, maybe the array list. You're using so many library classes, right? Now, the question you want to ask yourself is, are the library classes, reliable? Because in some way, for your implementation to be reliable, it's not just about your part of coding works, but also the library classes might work too. How confident are you? So now, in this case, you may have to do some additional work to make sure that that's really reliable. Additional verification might be needed. But in this case, maybe we wouldn't have to go that deep into something formal. You can do some exhaustive testing of the library methods to make sure they work. That will be okay. Okay? Testing. Right? So this is to say, whenever your implementation depends on other people's work, it will be up to you. Do you trust them faithfully? You don't worry about their reliability. You just assume they are reliable. Or if you want to go over their implementation as well thoroughly and formally verify it, if you have that time and efforts, or maybe you just want to test it, it will be your call. Okay, I want to bring that into the context. That's about verification. And finally, I want to talk about validation. For validation, it's really about this part over here, informal requirements. So basically, the same picture over here, but for validation, we are being critical about what's really given over here. For validation, we want to be critical. on what's given. In this way, we want to see if there's any ambiguities in the informal requirements, if there's any contradiction, if there's anything that's missing from the requirements documents. Right? We don't assume them anymore. We're going to go into the documents and say, now let's make sure we are building the right product. Okay. Guys, any question for this? Verification versus validation, right? Again, it's a very important context to know. All right, I think we got about 9 minutes according to my watch. I would suggest let's do some trial attendance checking very quickly. And then can we skip? Oh, sorry. I hope you're happy, right? Let me make sure. Good. So let's now do the check very quickly. Can we skip the break just for today? Let me just cover one or two more concepts, and then I can let you guys leave a little bit earlier today. And then we'll start from scratch next time. Okay. How about we do some attendance checking? Let me just stop the recording for now as a break. Alrighty, so one more stuff to cover, just one. So we talk about verification and also validation, right? Please go over the notes. It's basically everything we have covered. And then I'll start with this slides maybe next time, okay? That's about the sign effect. I want to go over one more thing. Okay, that's good. We'll start from here next time. Let me go over one thing on the iPad, and then we're done. Okay. Again, this is something that's also optional just for your information. So there is a keyword over here you may want to be aware of, which people also talk about in the industry. It's called assurance cases. Okay? Assurance cases is also an attempt to certify critical system. If you're interested in what assurance cases really is, you can feel free to research on that. It's optional, not required for the course, right? I want to give you some very simple example. This diagram over here, which looks like a tree. Usually assurance case is like a tree. You go from the root and then all the way down to the leaves. And if you want to go a little bit deeper into this particular example, there's a source over here. But I'm going to give you something much simpler just to get a feel. Usually, the way you structure the assurance cases to prove a system is by start with some overall claim. The claim may be supported by subclaim, which you can try to argue separately. And then for this particular claim, maybe I'm able to prove it by using some evidence. And the evidence over here does not have to be 100% formal. It's just a way to structure the argument. Let me give you one example. It may be that you want to show that your particular system is really fit for use. That's the claim I want to do overall. And now, how can I divide the fitness into two subclaims? Let's say I decide to do the following. Number one, my system should be correct. Number two, my system should be efficient. So I'm basically saying this and conjunction this should imply fitness, which not necessarily is formally true, but that's just the way assurance cases work. You want to provide some tree structure that seems convincing, not exactly formal, right? That's a big literature actually for assurance cases. So let's talk about correctness over here. So over here for correctness, how can I provide evidence? To be honest with you, here can be quite a variety of evidence that you can provide. You can say I got exhaustive testing. Maybe I have verified everything rodent, right, etc. So I'll give you some example here. It could be, for example, rodent, or it could be some testing result. Okay, and then finally, how do you prove that it's efficient? One of them could be, for example, you do some asymptotic analysis. Oh, sorry, let me see that. Efficient, I can say my claim is it's big O of n log n. That's a claim, right? Now, how do I provide evidence? Maybe I can give you the asymptotic analysis of the algorithm to show that it's big O over n log n, okay? And etc. So that's the essence for assurance cases. Again, not required for the course, but you're welcome to do a little bit of research on that to find out yourself. Thank you so much. good for now. And then on Thursday, we'll finish the last bit, and we'll definitely start with the math review.